So an interesting thing happens when you take the divergence of r hat over r squared. And this will lead into the Dirac Delta Function, which makes our lives a lot easier when we consider certain problems. So let's consider what happens when we have the divergence of this field r hat over r squared. So when we use v vector equals r hat over r squared, obviously we're working in spherical coordinates. And what happens is basically the farther you get away from the origin, the vector field gets smaller and smaller really rapidly, and it goes towards zero. But as you get closer, the magnitude, the length of these vectors get longer and longer and longer until at zero it just blows up, right? Because at zero we don't know what the vector field is, so you can't divide by zero, so it just doesn't make any sense to have that like that. Well, we can go ahead and try to calculate the divergence of this field though. So plugging in the stuff we learned from spherical coordinates, we take 1 over r squared d by dr of r squared times the field, so that's 1 over r squared. Or rather, not the field, but the r hat component of that field. And solving for that, it should be rather obvious. These two terms cancel, so we get 1 over r squared d by dr of, well, 1. D by dr of 1 is 0, so the whole thing is 0. So the divergence is 0. And there should be alarm bells going off in your head right now, because what I've done is I've actually divided by r squared not once but twice here. And when you're dividing by r squared, this doesn't work for r equals 0. So we don't know the divergence at the origin, but anyway, we're going to play stupid and pretend that that's 0 as well. We're going to forget that we divided by 0. Then we apply Gauss's theorem, where Gauss's theorem says that the volume integral of the divergence of some field times the volume element is equal to the surface flux of that field dot dA vector. Okay. So for the surface, so obviously this is supposed to be 0 because the divergence is 0. So if we considered a sphere centered at the origin with the radius r, then this formula becomes much easier to write. So this becomes, so we're going to do sphere radius r. Okay, so the vector is 1 over r squared, r hat, okay? And this dA component is r squared sine theta d theta d phi in the r hat direction, okay? So the dot product of those two, because we're taking the dot product, well, we just multiply the two components together. The r squared components cancel, so we get the integral of sine theta d theta d phi. And breaking that apart, so we're going to go from theta equals 0 to pi, right? Because if you start pointing straight up, that's theta of 0, and as you point all the way down 180 degrees, that's theta of pi. So we're not going to wrap around. We're not going to take a double sphere. Sine theta d theta, and the integral phi equals 0 to 2 pi, because phi represents how far around. That's a whole circle that you can spin that thing around as a whole circle of d phi, right? So derivative of sine is a cosine, derivative of cosine is negative sine, so this is negative cosine theta divided between pi and 0, and this is 2 pi. Okay, and so we get cosine of pi is negative 1, so we get 1 minus 1, so we get times 2 pi, we get 4 pi as the flux through the sphere of radius r, of radius capital R. So this is surprising. So the divergence we calculated was 0, but the flux is 4 pi. And the reason why we've we've proven basically that 0 equals 4 pi is again, we've been dividing by 0 the whole time, and we pretend like nothing's wrong with doing that, and of course it is. It just doesn't work out that way. So that's the problem. Problems like these are the ones that spurred the invention of the Dirac Delta function. And if you study quantum mechanics, if you study other fields, you're going to run into this again and again and again. So anyway, that's the problem that spurs it, and we're gonna use the Dirac Delta function to solve this and make everything make sense.